Welcome, everyone. Thank you for joining us today. My name is Adam Galata. I'm the Marketing Manager for the EMEA region at Monolithic Power Systems. Today's presentation marks the beginning of our April webinar series on industry trends and solutions. I'm joined by Christian Cook, our Senior Field Applications Engineer and EMC expert at MPS, where he will be presenting key spread spectrum techniques to reduce EMI. Just a little housekeeping before we get started. If you have any questions during the presentation, please type them into the question box in your Zoom control panel. I'll bring them up during the end of the presentation during our Q&A session. All of the webinars are available for on-demand streaming at monolithicpower.com. Today's webinar will be added in a day or two, and I'll also be sending out a follow-up email with links to the presentation materials and video recording. Now, without further ado, we will turn it over to Christian.
Hello, my name is Chris. It's now probably 25 or over 25 years. I was 22 years at Linear Technology and on a similar role. And most of my time I spent supporting power supplies for the industrial, automotive, medical industry. And one of the major concerns was always EMI. And one thing which can have a big impact on EMI is spread spectrum. And that's the topic we talk today. First, the agenda is I talk a little bit about the motivation. And to understand that, we have to talk about what a fixed frequency power supply spectrum is. Then we talk about the effects of switching frequency and duty cycle on the EMI. Then what can spread spectrum really buy you? And what methods do we have available to make spread spectrum? And then I go over typical frequency asked questions. And after that, we have an open Q&A. And there's on top button where you can put in writing questions, and Adam and I will then answer them point by point as good as we can. Okay, first to the motivation. Typically, if we have a fixed frequency switcher, we get individual spurs, and these spurs are spaced apart, typically by the switching frequency. And more often than we got spurs which violate any limits we get from our customer base. That could be whatever OEM limits, or could be legal limits you have. And now you have to do something on your designer to keep them below the limit lines, so that you pass regulations. One way what you can do is try to get or distribute the individual spur energy now to make the spurs looking smaller, and that is by modulating these individual spurs. And directly, if you modulate the fundamental, and for example, frequency modulation wise, you should always keep in mind now that the harmonics will also be modulated with the same frequency, but the span of these spurs is multiplied. So the first harmonic has double the modulation span and 3 times, and so on. Now we'll see later in examples. On fixed frequency power supply spectrum is in the low frequency range remarkably flat. So you can see that over frequency span maybe up to 300 megahertz, it only dies down maybe 10 dBs. Now that's not much. Now you can also see now that the individual spurs are always multiples on the switching frequency. If you look a little bit further out, now we can see, okay, there is a point when energy of our switch node edges drops down. Here in this case, it's in the range of, say, 500, 600 megahertz, where it really dies down. Now, that are some artifacts because I have a GSM station in my area, and it's really difficult to shield for them. But there is an area on a typical switcher in the 700 megahertz range, 500, 600 megahertz, where your energy drops down, so you don't have a problem usually what goes above 1 gigahertz, because on a decent design switcher there shouldn't be any energy left on the edges. Now let's look how the lower harmonics look if I change the duty cycle of a switcher and the input voltage. So the yellow line is the switch voltage. And if we start that video, we can see that we get a nice fence up to 10 megahertz. And as soon as we increase the voltage, you will see now that the Spur energy differentiation. And there's a point where every even harmonics actually disappear. Now that's roughly where the input voltage is double the output voltage. So you in a 50% duty cycle area, you have all the even harmonics disappear. Now, so a duty cycle has an effect on the lower harmonics. Now, so don't be surprised if you do lower harmonics measurements, now that it will be dependent on the input voltage. And if you go high with the input voltage, you also see now that the spurs go higher. Now, so the spurs definitely track with the input voltage. So as high as the voltage on the switch node, as higher the spurs. Now that's also a general takeaway from this experiment. So at 50% duty cycle, all even harmonics disappear, as Fourier transformation would also tell us. And the lower harmonics depend on the duty cycle. So if you compare really EMI results for low harmonics, make sure that the input voltage is the same as in former comparable measurements or whatever your customer specification says they should be, because it will depend on the switch voltage you have. And also a takeaway is that the harmonic energy goes up with input voltage. If you think, okay, now what does switching frequency to our harmonics contains? Now, so we start out with a 500 kilohertz switcher. Now, so we see the harmonics evenly spaced. Now we keep it at 12 volt, and now we increase the frequency to a megahertz, and we see that the spurs go up. Now they are now spaced with the megahertz, but individual spurs goes up by roughly 6 dBs for doubling the frequency. And if you go even higher to up to 2 megahertz, then we'll see now that the spurs now are about 12 dB higher now than compared to a 500 megahertz case. Now, so if we double the frequency, you can keep in mind now you get usually 6 dB worth EMI on a fixed frequency switcher. And also the spacing goes up as we could expect now with the switching frequency. Okay, what happens if we look in a broader frequency range? So if you look up to 300 megahertz, now here I use the resolution bandwidth, the EMI resolution bandwidth of 120 kilohertz, which is in effect for any frequencies up to 30 megahertz. To get a real picture, we start at 500 kilohertz. Now the red line shows you here the frequency, and if you go up to a megahertz, you see now that wide band, now we got 6 dB more. Now it's now 5 dB per division here. And if you increase the frequency up to 2 megahertz, now we have roughly wide band 12 dB more. Now, so really EMI goes proportionally up with switching frequency on a fixed frequency switcher, roughly with 6 dB for every doubling of the frequency. Let's see if you go back to 500 kilohertz, so we have the original curve again. Okay, in general, an EMI is measured by an EMI receiver, which is which behavior is specified in CISPR 16, and in general consists of an input and attenuator stages, a few mixers. Now that depends on the special design, and it doesn't matter if you take an ordinary EMI receiver, a spectrum analyzer, or some modern FFT receiver. Now they generally behave and look pretty much the same. And what's the most important filter we face for our EMI work is the resolution bandwidth filter. So at the end of the mixing, there is a resolution bandwidth filter, which is according to the standard CISPR 16 and most other standards are 9 kilohertz for frequency range below 30 megahertz. That comes still from the old AM audio station bandwidth. And for frequency above 30 megahertz, typically it's 120 kilohertz. There are some certain ranges where they measure even with 1 megahertz resolution bandwidth to make life even more harder. But that's the typical two frequencies you will face, might be with 1 megahertz. And this filter is actually before the power rectifier. No? So here, the power rectifier takes the energy out of your signal, integrates it, and after the power rectifier comes then the filter, which goes to the annunciate instrument, which says, okay, it's peak, quasi-peak, or average. So that all happens after rectification, after power integration of your signal. So your resolution bandwidth filter is before that, and it has this effect on all these filter wishes. In general, it's specified as a bandwidth filter, and the typical spectrum analyzer filter would be specified as a -3 dB. In EMI filter, due to historic reason, is specified as -6 dB corners, but it doesn't matter much. It typically looks that way, and there's actually a standard you can download here from SWASpec, which has pretty good information about that. Okay. In general, on a fixed frequency switcher, we got spurs, individual spurs, which are spaced with the switching frequency. And we move our EMI receiver as an old radio with a turning knob through this frequency range. And actually, what it resolves is the resolution bandwidth around these spurs. And so in general, what the EMI receiver does is a convolution operation in the frequency domain, that your resolution bandwidth filter is convoluted over your spurs. And if you do that, now it looks away now that every individual spur is actually widened up by the resolution bandwidth filter. And in order to hide some energy, your EMI receiver will not see and will not detect there's some area between these spurs. And that's the area where any spread spectrum technique can hide the spur energy to get actually the peaks down. So that's how in general any spread spectrum works. And you try to widen up your frequency domain, and in optimum make it like white noise and constantly energy distribution over frequency. So that's the optimum case. And if we know that, we can actually calculate what the maximum attenuation is spread spectrum can accomplish. So for 9 kilohertz resolution bandwidth, we can calculate that, for example, for a 400 kilohertz switcher, the maximum attenuation spread spectrum could do is 16.5 dB. For a 2 megahertz switcher would be 23.5 dB. If you go to the higher resolution bandwidth, so the area above 30 megahertz, then spread spectrum can buy us only 5.2 dB for a 400 kilohertz switcher and 12.2 dB for a 2 megahertz switcher. So the benefit of spread spectrum goes down with higher resolution bandwidths. So at 1 megahertz resolution bandwidth up to a megahertz switcher, there's no benefit at all. So you can't expect something. Okay, there are several things which determine how the real attenuation of our spread spectrum modulated signal is. And one is how long our spur actually stays within the resolution bandwidth area. So even any individual spur, how long does it spend its time, because it's remodulated and moving around, how long does it spend its time inside the resolution bandwidth? And in order to get any attenuation at all, it has to move through these resolution bandwidths faster than the step response of the bandwidth of the resolution bandwidth filter, which means that if we keep our spur 111 microseconds in a 9 kilohertz resolution bandwidth, we don't get any attenuation at all. And 120 kilohertz resolution bandwidth is even tougher, so we have to spend much less than 8.33 microseconds within the resolution bandwidth. Otherwise, now we don't get any attenuation. So that gives us a limitation on our modulation scheme, so that for resolution bandwidth of 9 kilohertz, the spurs have to move faster than 81 megahertz per second in order to get any attenuation. And for 120 kilohertz, they have to move faster than 14.4 gigahertz per second. No? So that's actually a matter of frequency change. No? So they have to move faster around. You can also put normal FM modulation theory on it, and for an FM modulation and for spread spectrum power supplies, typically FM is the only decent modulation scheme you can use, because typically you want to have constant output voltage, which means constant output power. And if you modulate a carrier and you want to get a constant power, no? So you don't want to have any amplitude modulation, because that would give you direct output ripple. So you have to resort to frequency modulation. Fortunately, frequency modulation spectra are fairly well understood. And for a sinus frequency modulation, there are two things which determine the outcome. One is the modulation depth, now, which means how far do I move my carrier? Now, so what's the difference between maximum and minimum frequency? I call it modulation depth, or the stroke or span of the modulation signal. And with the given modulation frequency, so what would be the low frequency you put in now, where you move your carrier around with, you can calculate a modulation index, which is simply the modulation depth or span divided by the modulation frequency. And keep in mind, since the modulation depth, the moving around, goes linear up with harmonic number, the modulation index goes up by itself for any harmonics. So if we look from modulation theory, what attenuation in FM we can get, now we see now that we have over the modulation index, we have to have a fairly high modulation index to get decent attenuation. No? So low modulation index does not help much. No? So it should be in the at least in the 2-digit range. Otherwise, no, it doesn't help much. We can actually make an experiment to it. So here I have a modulation signal which I can move around, and here I have the carrier. The resolution bandwidth is 9 kilohertz, and now I actually increase the modulation span, I think, to 20%, 20%, and I start with a very high modulation frequency of 122 kilohertz. So I get actually only 2 spurs. If I move the modulation frequency down, now I see the spurs become more narrow now, and I get additional spurs. So I can immediately see if I have a very high modulation frequency, which is a low modulation index, I get only a few spurs. As the lower I get with my modulation frequency, as more spurs I get, as more attenuation I become. However, there's also a border. Here we are now 7 kilohertz, and if you go further down, we see now that at least first at the edges, attenuation actually goes down again. So we don't get that much attenuation with very low switching frequencies, modulation frequencies. So there's actually seems to be an optimal modulation frequency where we get the best results. And it's astonishingly around the resolution bandwidth itself with our modulation frequency where we typically get the best results. So that's about 10 dB of attenuation where we get. That's a triangle modulation signal I use for this test. We can also look what the higher spurs do. So the first was only the fundamental. If you look now for the higher spurs and make the same experiment, now we can see it takes now a little bit up to 30 megahertz now for the EMI receiver or spectrum analyzer screen to go up. So if you go to 20% modulation with a very high modulation frequency, we see, okay, we get very little attenuation. We get something in the higher frequency range, but as soon as we go down with our modulation frequency, stuff looks much better now. And we get our 12, 15 dB attenuation. So even in the area around the resolution bandwidth, it looks quite good. The least attenuation we usually get at the fundamental, and as higher we go with our harmonics, as wider the span goes, you can see. And here we have an overlap region. In the overlap region, actually at a certain point, it doesn't change too much, but we see here with lower and lower modulation frequency, at least at the fundamental and the first harmonics, we get less and less attenuation. So if you go back here to our more decent point, 9 kilohertz, now we see now that actually our spread spectrum buys us more attenuation. That's our experiment. If somebody has an EMI receiver or spectrum analyzer, you can actually do that. And so on. If you go back to the fixed frequency situation, we have the original curve. Okay, what happens with our attenuation if we change around the modulation span instead? Now we also look same screen with 30 megahertz. Use the optimum modulation frequency and now use a very small modulation span. You can see now as high as the harmonics go, as high as the individual span goes. If you go make them down, get less attenuation, smaller spans. Now, so you can immediately assume that more span is better. So a 10% span. You almost get in the overlap region the maximum attenuation, but where it helps is in the fundamental and the first few harmonics. Now, if you increase your modulation span, in theory, an extremely high modulation span would be best. However, that puts also some limitations on our regulation loop from the switcher. So at a certain point, the output ripple will go up because your loop regulation can't keep up with very high changing modulation spans. Now, so you see in the overlap region, very high modulation span doesn't buy you much additionally, but in for the fundamental, so you get a lot more. If you look what's in the 120 kilohertz resolution bandwidth range, so valid for 30 megahertz up to 108 megahertz, it's a typical conducted emission area. And we look what spread spectrum buys us there. Since we have 120 kilohertz resolution bandwidth, we can assume that we get less attenuation. We can see that now. If we have 5 dB per division now, it does this by hardly 5 dB, even if we go with a very high modulation frequency. And if you go down with modulation frequency, typically we get less and less attenuation. So as expected, it's very hard to get a lot of attenuation as wide a resolution bandwidth gets. And we can't argue because the standard, the CISPR 16 standard, sets the resolution bandwidth to 120 kilohertz in that area. And if you do very low modulation frequency, we see some spurs ticking up to the original signal. So you can assume that if you make a peak measurement and put it on peak hold, you will get very little attenuation. So 120 kilohertz resolution frequency, actually very high modulation frequencies up to 120 kilohertz would work best if you could afford that, if your switcher would work with that. Okay, in general, what we learned is that around the resolution bandwidth frequency, you get the most attenuation, and you get less and less attenuation if you go down with the modulation frequency, because your resolution bandwidth filter impulse response prevents the spurs actually stay too long inside the resolution bandwidth filter, so you get no attenuation from the resolution bandwidth filter. If you go higher with the frequency, your resolution bandwidth filter is happy. However, you have get into the area, especially for low frequency, for the low harmonics, where you have a low modulation index, which means you get too few spurs with too much individual energy, and you don't get much attenuation. So there is an optimum of modulation frequency for each resolution bandwidth range. Now, so again, high modulation frequency gives a low modulation index, low modulation frequency gives low resolution band filter impulse response. And typically, since spread spectrum buys you most in the below 30 megahertz area with 9 kilohertz resolution bandwidth, and they're as toughest to filter, it's best to optimize for the 9 kilohertz resolution bandwidth range, because here you get the most reward in the lower frequency range. Now, we talked about modulation frequency, and we didn't talk yet about modulation waveform shape. No? So what we know, it should be a constant velocity in hertz per second, and a high number of frequency change would be good. However, that is a problem, because, I mean, you could start at a certain frequency and you go to infinity, a little bit like Zigbee. However, in a power supply, there are some limitations, so you have to stay in a certain frequency range. So no matter what, your modulation signal has to be periodic. And one simple periodic modulation signal would be a triangular. And here in the normal steep slope, you get an constant frequency change on a given time. The only problem occurs if you change direction in your signal. So in the same time, you get only half the frequency span. So you spend only half the, or you move through half the frequency in the turnaround points. So that's a little bit of a problem. What you also could do, use a real sawtooth signal. So here you have an equal change of delta Earth in a certain time signal, and here in that sharp edge you get an infinitive frequency change, which from signal theory isn't a problem, or from modulation theory. So if you could do that, no problem. However, the problem is most times that for the switcher regulation loop, it's very difficult if you get an instant frequency change, which most times goes hand in hand with an instant duty cycle change, which most regulation loops won't allow. So even so, from a theoretical side, a sawtooth signal looks promising. It might create more output ripple than you like. So what you could do is, you could take a normal triangle and steep it up, make it a little bit peaky, so that in the turnaround area, you make the same frequency change, and that's called an Hershey kiss. According to a chocolate you can buy, would look similar. Or you could make actually a step signal, a sharp step, and then have a modified modulation. However, it's in a lot of cases questionable if it's really worth going to that wide. Most times a normal triangular signal will do just fine. Actually, if you have a switching regulator which is fixed frequency and has an external frequency setting resistor, like a lot of our parts do, like the MPQ4430 family, and as a frequency resistor externally sets the frequency, you can easily make it spread spectrum just by removing the fixed frequency setting resistor, and you replace it by a resistive divider, and on the bottom you just put a rectangular signal and shape it into a triangular signal with an RC. So if you have any signal source, or microprocessor, timer, or whatever rectangular source in the neighborhood of 9 kilohertz, and even if you have, say, 1 kilohertz, it's better than nothing. You can make, with a few O4, O2 components, a nice spread spectrum signal. So here at that point, you get a nice, pretty much triangular shape. So for spread spectrum, it will do. And here, that's the actual result of a 4430. Here, that's a fixed frequency area, and here the spread spectrum results. So with a few very cheap components, you can buy a lot of EMI improvement if you have a fixed frequency switcher which actually has an external frequency setting resistor which works analog. Also, it doesn't matter, you can also digitally control the loop. So we have a part here which has an I2C interface, and you can run its spread spectrum. Now here it's fixed frequency. So if you change the modulation frequency and reprogram it, you can easily set it into spread spectrum, and you can play around with modulation frequency and the modulation span, for example, and you get then different results. Okay, so we have lots of parts which have a digital oscillator and an I2C interface, so you can program these things. Spread spectrum benefits. So the good thing is spread spectrum is a frequency method, and it works independent from any other EMI mitigation method, like filtering, layout, shielding. So you can use a fixed frequency switcher and make an optimum layout. If you do spread spectrum to it, you get the additional dB, no matter where you start. So it always works in addition to the other methods of EMI improvement. A good engineering practice is if you can develop and test your power supply, especially also on stability and so on, in a fixed frequency setting, because there, if you look with the scope on the switch node, you can see any, say, instability issues. If you already started with spread spectrum, with the switching frequency and duty cycle moving around all over the place, it's very difficult to detect on the scope if you have an actually instability area or it's just the effect of spread spectrum. So it's best if you can switch through your spread spectrum on and off. A lot of our parts, which even have a fixed spread spectrum, have a synchronization pin where you can put an external signal to it. And in general, spread spectrum adds minimum output ripple to the fixed frequency signal, as long as your regulation loop is fast enough. So, and if you have non-fixed frequency loop topologies like COT, hysteretic, you might not see anything in addition. A typical transient response is also not affected unless you use excessive frequency spans. We learned now that EMI goes general up with switch voltage by 6 dB for every doubling the switch voltage. So it means for a low voltage switcher like 5 or 3.3 volt input bucks, where you make your usual core voltage or whatever voltage you need, you can easily get away typically with over 2 megahertz switching frequency, because the EMI content of that thing is not that large, because you have benign switch voltage moving around. So you can keep the inductor small and low profile and don't have much EMI problem. But if you have higher switch voltages like 12 volt and more, you should usually keep the switching frequency as low as practicable. So in most cases, it means sub-AM band. Otherwise, you create a lot of EMI problems. Since EMI goes up 6 dB on a 6 frequency switcher for every frequency doubling, and even if you make a perfect spread spectrum, you can only get 3 dB back from the spread spectrum version. So you still have a penalty of 3 dB for every doubling, even for a perfect spread spectrum switcher. Frequency synchronization externally. The oscillators used in the typical switchers are RC type of oscillator. So they have some inherent phase noise or frequency modulation, and the phase noise multiplies by the harmonic number. So if you start with a low frequency, say 400 kilohertz, so you get some natural frequency modulation due to the phase noise. If you then think, you can synchronize your switcher with a clock oscillator with crystal or so, you lose that natural FM attenuation. So it might get worse that all of a sudden you have really individual spurs you can see, where in normal operation, maybe a special, for example, on a COT switcher, which has even more natural phase noise, because duty cycle and the switching frequency will depend on load current and these things. So you can get some spread spectrum effect for free if you sync them or force them to sync to a high quality oscillator. The high spurs might come up. So sync it only to a high quality oscillator when it's absolutely necessary from your system. It could be that you have some special high-speed A to D converter, and you have to synchronize stuff no matter what, then you have to do. But if not, it might not buy you anything. It might make stuff worse. So Spread Spectrum is an excellent tool to reduce EMI with very little additional cost. Optimal modulation frequency we talked about is around the resolution bandwidth frequency. And typically, most times you get away if you optimize for the 9 kHz resolution bandwidth. And with Spread Spectrum for lower frequencies, typically the cost savings on the input filter is the highest. You should test your power supply on fixed frequency if you can. And you can move frequency setting, fixed frequency parts, which have a frequency setting resistor. Pretty easy to make a Spread Spectrum with only a little additional effort. And excessive frequency spans only helps on the first few harmonics. In the overlap region, they don't help you much. So, and in the 120 kilohertz resolution bandwidth area, so above 30 megahertz, it's very difficult to get much out of Spread Spectrum, as we learned today. So go to some typical FAQs. Now, how many dB reduction I can get? So it's a reminder, okay, 9 kilohertz resolution bandwidth, 400 kilohertz by 16.5 and 23.5 and 2 megahertz switcher. So it can really be calculated. Does Spread Spectrum affect the transient response of a DC buck-to-rate? Very little. So because typically your loop is fast and the change in duty cycle due to spread is benign. Which algorithms can you generate to use Spread Spectrum? In general, doesn't matter. If you make it analog or digital, as long as you change the duty cycle every pulse, every cycle, physics cannot distinguish if you make it digital or analog or any way else. What frequency modulation envelope is most effective, sawtooth, triangle, or sinusoid? Sawtooth or triangle are pretty effective. Sawtooth might be a problem for your regulation loop. Sinusoid is not that good because on the top and the bottom of the sinus, you spend pretty long on the same, say, frequency if you make FM out of it. So sinusoid should be avoided. So don't linger around at a certain frequency point long enough. I hope we learned it today. What's cost difference? Typically, inside the effort is not very high on the switching regulator. There's some area involved, but it's only a few percent of the total switcher area. So you can get a lot with very little effort. Does Spread Spectrum really help EMI, or is just cheating the test equipment? I mean, in general, the energy you create is the same. It's just distributed differently over the frequency. So it's more a philosophical question. Yes, you say your EMI receiver will see less spurs, but that's what your customer usually pays you for. You have to pass limits. That's how you do it. He doesn't care. For which kind of EMI Spread Spectrum does help? Of conducted emitting, radiated emitting, client to 30 megahertz, greater than 30 megahertz. Since it's a spectral method, it helps on all conducted and radiated emissions, and it depends on the resolution bandwidth where it helps more or less. Now, I think we covered that today. Are there any secret military or patented Spread Spectrum methods which get more attenuation? So go back to our table. Even for the military, still physics applies, and even also for buyers. So you can calculate. There's only so much physics can do for you. So we had that on the table. So there isn't any secret stuff which does more than physics. Pseudo-random. Now, we didn't talk about much, but we saw that there's an optimum modulation frequency. The problem with pseudo-random is that in order to make it effective, you would have to limit the bandwidth of your pseudo-random signal that it doesn't include too low or too high frequencies. And that's pretty tricky. Now, if you do it pretty optimum, then your modulation signal actually will look pretty much like a triangular signal. And so typically, it's much easier to make things worse with pseudo-random compared to a simple analog triangle signal. In order to support our customers, we put a lot of effort in EMI. Now, we have already an CISPE 25 EMI lab in China, Hangzhou, and we are building now a lab in Germany, in Ettenheim. The first vaults you can already see there. Now, so we hope that we get it operational end of this, start of next year, and we have an fully qualified SAC chamber for automotive industrial consumers. We have a CISPE 25 chamber. We have a additional shielded chamber and got all the equipment for pulses and application engineering tests. Now, so if you have any EMI problem, you can, that's the plan, use our facilities, and there will be probably a difference on pricing. So if it involves an MPS part, it will be free or pretty cheap. And if there's no MPS part involved, then certainly you can do that, but then you have probably to pay for it. Okay, so there's some attachment. Okay, now we open it up to the Q&A section. Adam, you are still there?
Yeah, thank you, Christian. We'll go ahead and take some questions now. Just a reminder to everyone in the call, please sure to type in your questions into the question box located in the Zoom control panel. It does look like we have an initial question here from Paul Lopez. He's asking, considering a DC-DC converter with a certain efficiency, if a spread spectrum technique is used, how does this affect the initial efficiency?
Very little, because you change the switching frequency around like 10 or 20%. And in the efficiency area, you normally don't notice that. No? So it would be in the ppm range. No? So effectively zero effect. You know, it doesn't matter if you go fixed frequency or spread spectrum, because you move the main frequency only a little bit around, and you have to change the frequency much more to get an really visible effect on efficiency. Sure, if you double the frequency or quadruple, then you get a lot of different loss terms. But if you move it around 10 or 20%, it usually you can neglect the issue.
Okay, are there any other questions? You can put that in the question and answer box. If not, we'll wrap things up. Okay, thank you everyone. We appreciate you being here. If you have any further questions regarding spread spectrum, or if you'd like to learn more about our EMC lab that's being built in Ettenheim, Germany, we will send out a follow-up email after this webinar within 24-48 hours. Thanks again for joining us today, and we'll see you next time. Bye for now.